So, Ribu, I am recording the class, okay? All right, guys. So, did you guys prepare, go through what we discussed in the last class?
Sir, I read through the textbook.
We showed the experiment and all, huh? I think this is what we discussed last, right?
Yes, sir.
Yeah.
Okay, so let me. Are you able to see the presentation, guys?
Yes.
In the full screen mode? Okay. Ribu, can you please confirm if you're able to see the presentation in the slideshow mode?
Yes, sir.
All right. Okay. So this is what we discussed, and you guys have taken down this diagram also. Sound travels in a series of compressions and rarefactions. This is what we discussed. Then what we will do is we'll move to the next representation here. Okay. Can you see the animation that is happening in the screen?
Yes, sir.
So, Aditya, what are these red dots? Can you just explain to me what you're seeing?
Sir, there might be particles of matter.
Particles in air, okay? When we are talking about sound propagation through air,
Yes.
these are particles in air. And can you see, can you tell me what are the red dots doing basically?
So they're traveling through a medium.
Just to check properly what the red dots are doing.
Sir, I think what's happening is that as a compression is coming, they're getting it's getting
Simple.
propagated.
What are the red dots doing? Look at only at the
They're
red
moving,
dots.
sir.
How are they moving? How would you describe their motion?
So they're vibrating and going through a medium.
No, check again.
They're getting
What are-
compressed.
Just look at the red dots and tell me what are the red dots doing?
Vibrate about their mean position.
Red dots are moving to and fro, isn't it? Like a pendulum, they are swinging from one position, right position to left position. Okay. Red dots are not going from left side to right side of the screen completely. They are just going, swinging like a pendulum from, one extreme position to on the right hand side to one extreme position on the left hand side. Shreya, do you agree to that, ma? Tanush, do you see what I mean?
Yes, sir.
Okay, that is our first observation is the red dots are moving left to right. Now, what do the red dots represent? Are they anything special?
They are particles of matter.
So these red dots are just a sample of the particles which are in that zone, guys. Okay, we didn't take the. Just give me 1 minute. Hi, Pallavi. Hi, how are you doing? Yeah, no, we can speak for 5 minutes, no problem. Hmm. Sorry about that, guys. It was an important call. I had to take it. Okay. So the red dots, no, they are like representatives, like the class leaders for all the particles in that zone. Okay. So that if I say look at all the black particles, means you will get confused. But if I say, hey, the red dots are representatives of them, you see how the that particular zone is moving, right? Then you get to understand, right? So now if you see, the entire thing is like on the left hand side, we have the drum or the membrane. So that membrane is coming this side, and then it is pushing all the particles too close together. So you see that a region of high pressure developing. The black line is developing, and then it looks as if the black line is progressing forward, isn't it? But that black line is not the particles physically moving from one place to another. The black line, which is the compression, is the compression is progressing forward. But how did that compression come about? Because of the oscillation of the particles in the medium. Are you able to follow this, guys?
Yes, sir.
Okay, so even if here, for example, if you see this place, right, the black particles also are moving, oscillating to and fro only. Okay, but that oscillation over a period of time is transferred from one zone to another zone, second zone to third zone, and then you see that one black line kind of a thing which is going forward. That is the high pressure region. Okay, and then in between, if you see, that becomes a low pressure region. So low pressure region is not one particular straight line, right? It is spread over. Okay, so that is what the rarefaction zone is, a larger zone, compression zone is a smaller zone, and we see that compressions and rarefactions are moving forward. Okay, do you kind of get that sense by looking at this animation?
Yes, sir.
Okay, all right. So the yellow line on top, along with compression, right? So that kind of showcases how that entire compression zone, that's starting now, this how the entire compression zone is moving forward, right? Without the particles actually moving, it is just that the particles are oscillating, creating the compression zone, and the compression zone is moving from one position, left hand side to the right hand side. Okay, and then the purple line is the rarefaction. Rarefaction means low pressure zone. The low pressure zone also seems to be moving from left to right. Did you get that?
Yes, sir.
Yes, sir.
Now what you do, you look at the graph below. Okay, so what we are trying to do is this top zone is there, no, compression zone. This compression zone's pressure we will measure, or rather what I will do, I will take you to a different screen. Okay. Okay, are you able to see the screen, guys?
Yes, sir.
Where this dark thing is the high pressure region. Okay, so if I measure the pressure in the high pressure region, let us say some 10 pascals are there. Okay, and then I plot that high pressure in the form of a graph. Okay, so that forms the peak. So if you see that in the first graph, okay, so that high point is matching the highest pressure in the bottom graph. Just give me 1 minute, I'll try to annotate here. Please let me know if you are not following, okay? Okay, give me 1 minute. I'm sharing my OneNote now. Can you confirm if you're able to see this, guys?
Yes.
Okay, so what I am saying is this is a some high pressure zone. I will say capital P. This is like a low pressure zone. This is the rarefaction. Okay. So once again, this is the high pressure zone. Okay. So you have a series of high pressure zones and you have a series of low pressure zones. Okay. So what we are doing is we are trying to plot a graph here. Okay. And there is pressure on the y-axis. Okay. So in fact, let me take the axis properly and draw it for you. Give me 1 minute. So, are you able to see the axis, guys? X-axis, y-axis I have drawn.
Yes, sir.
sir.
Okay, just give me 1 minute. So, if I take this y-axis, this x-axis, okay, and I'm trying to plot pressure here, okay. So I'm saying, this P means high pressure. So I will take that point and I will put the high pressure point here. This means low pressure, okay. So low pressure means less pressure. I will put that point here. So once again, this is a region of high pressure. I'll put the point here. So if I do this, I can see, can you see me scribbling here, guys, on the OneNote?
Yes, sir.
Okay, so you will see that what happened above. Am I muted?
No, sir. That was before.
Huh?
Nothing, sir.
Okay. Just give me one. Oh, I understood. So, what happened? Okay, so if you see that this series of compressions and rarefactions which we are observing can be translated into this graph out here. Okay, by plotting pressure on the y-axis, and of course here we can say this is distance because this is the wave that is traveling. No, we can take it as distance. Okay, so actually what is happening? We are having this. Okay, this is the series of compressions and rarefactions, okay, of the medium. And what we are trying to do, we are trying to plot a graph. If you are able to plot a graph, okay, by taking the pressure on the y-axis and the distance on the x-axis. Okay, so this is going to be the peak pressure. Peak pressure of compression zone. And this will be the low pressure. Okay, this will be the low pressure of rarefaction. Okay, I want you to take a minute and kind of draw this. Without this, you don't need to have this graph there. Just draw this light lines and the compression zone and rarefaction zone. Okay, and then on top of that, you try to draw the graph and have this worm kind of a graph. Okay, where you show that this is the pressure of compression, this is the pressure of rarefaction. Let me know once you're done. Vibhav, are you having any questions? Or is it all fully clear?
Yeah, it's fine, sir.
So clear.
What about you, Shreya? Any questions, ma? Okay. Nandu, Aditya,
Yes, sir.
it's all clear, no?
Yeah, sir.
Shall I move ahead then?
Yeah. Yes, sir.
Ribu, have you finished noting down?
1 second, sir.
Huh?
1
1
second.
second, okay.
Yes, sir.
Okay. Aryan also has joined now. So that is what is this entire graph about, okay? So we are trying to capture the essence of the compressions and rarefactions in the form of this worm. In fact, this graph is also, the shape of this graph is called sinusoidal, okay? SINUSOIDAL. I'll write it down for you. Because this increasing decreasing graph is there. No, it has got a name. It is called sinusoidal. Okay, it is like or basically it is the form of a sine wave. Have you heard the word sine before, guys? SINE, sine? Sine, cosine, tan, cot. Aryan, you have heard of sine or not?
Yeah, sir.
But he's in mute, no? Shreya, do you know what a sinusoidal wave means?
No.
Yes, no, what?
No.
Hey, what is he saying?
So she's saying no, sir.
So she
No.
said,
Okay, so basically, do you know what sine theta, the trigonometric function sine theta cos theta, Shreya? Hey, CBSE guys don't know trigonometry, huh?
No, sir, but you taught
Sir, I just
basics
watched
in
the
one
video
class.
you showed, sir.
My video you saw. Okay, good.
You taught
So
in
what?
class also, sir.
Yeah, I know. So what happens is, if in trigonometry you have, okay, doesn't matter. We'll spend time for those who are not initiated later. But in trigonometry, you have what is called a sine wave. If you see the shape of it, it is like that. Upar niche it will happen. So any shape that has this kind of peaks and troughs and repetitive pattern is called a sinusoidal wave. The shape of the wave is called sinusoidal wave. Okay. Now let's get back to this one. Okay. We have to understand something from this, guys. Okay. So let's take a look at this in detail and address some of the characteristics. Characteristics means we have drawn one shape. What does the shape actually tell us? Okay. So, Aryan, I want you to see on the right hand side this sinusoidal wave and tell me what is it that you can see from here. I've marked something, no? What is it that you can see?
Sir, the amplitude.
Amplitude. What is amplitude? Can you tell me
Sir,
through
that's
what?
the highest sound of it.
No, from the graph, what is it you see? What have I marked as
Sir,
the
the
amplitude?
distance between the two points.
Say nicely, say properly.
Sir, the distance between the 2 points.
No, it's not the distance between 2 points. What is amplitude here?
So like how much big it is. What
Okay.
is the size of the wave?
What Shreya, can you try? What do you mean? What do you think is this amplitude?
so can I try?
Okay, Ribab, go ahead. Shreya, I want more participation from you, ma. come a little forward, be a little more, I want you to be a little more talkative. Don't be a passive observer, okay? Thoda aur energy laga ke you have to participate. Go ahead, Riba.
So like the distance from the baseline to like the crest and from baseline to the trough.
Baseline.
Oh.
So instead of telling baseline, Aditya, do you have any other word for it?
Median.
Mean,
Axle.
mean position. Okay. So you say this central line is there. No, it's like a mean position. So this wave from the mean position, the wave is rising, isn't it? So that is called the peak. So the distance between the mean position and the peak of the wave, that distance is what is called as the amplitude. Are you following this, guys? So
Yes,
Yes, sir.
yeah, can you just make a note of this particular graph? Draw a big graph in between, that wave in between. One by one, I will be telling you the various characteristics. I want you to make a note, okay? So first draw this graph and then let's discuss one by one. I'm sharing my OneNote now, right?
Yes, sir.
Okay. Let me know once if you're done with the graph. Okay, it's not just on top, even this fellow, this is also amplitude, okay? But don't tell amplitude is from the crest to the trough, okay? This highest point is called crest. This lowest point is called trough, T-R-O-U-G-H. The low pressure, the point corresponding to the low pressure, that is called lowest pressure rather, that is called the trough. The points corresponding to the highest pressure is called the crest, the peak. And then say amplitude is nothing but the distance between mean position and the crest.
So the crest is the highest.
Here I have made a note of this. See, this point is there. No, this peak is called the crest. Can you see the OneNote which I am sharing, guys?
Yes.
Okay, this point. Okay, in fact, this also is a crest. This is also a peak position. So we have got two crests here. You can say this is crest 1, this is crest 2. Like that, these positions are called the troughs. I will designate them by T1, T2. Two troughs are there for us. Are you guys done with this?
Yes, sir.
Okay. Then second thing is we want to say wavelength. Anyone knows what wavelength is, guys?
Distance traveled by waves in like one time period.
Distance traveled by the whole one rarefaction and one compression.
One compression, one rarefaction, isn't it? Or
One time period only,
there are
no?
Yeah, there are three ways we can say wavelength. Okay. This is like starting point. Okay. This is like ending point. Okay. So this distance between A and B is called wavelength. That is one definition. This entire thing is wavelength. Okay. So here I am writing distance between start of wave and end of wave. Okay, so now I am taking another measure. Okay, between this crest and this crest. Can you guess if this fellow and this fellow are one and the same? Or will they be different?
So they are the same.
They are the same, isn't it? So
Yes.
I will mark this guy in a different color if possible. Okay, so if you see between crest and crest, okay, also it will be wavelength. This also is called wavelength.
Sir, I have a doubt.
1 minute. Did you guys get the crest to crest? Okay, and this thing, this also is called the wavelength. Starting point, ending point is also wavelength. Okay, and tell me, is there any other definition for wavelength now that you can think of?
Sir, pro
So,
to
like I can tell you formula wise,
Formula
Sir,
beda.
is it
Just
pro to pro?
all that V is equal to F lambda, all that.
so this fellow, the trough to trough. Okay, I heard Aditya saying true. I like to call it as trough. Between the two troughs also is called the wavelength. Okay, so whenever you are going to talk about wavelength, okay, it is the distance from the starting point to ending point, or the distance between two crests, or the distance between two troughs. Any of these is the wave, the wavelength of the wave. But you have to say it is the distance between two consecutive crests. Consecutive, not first and fourth. Okay, two consecutive crests or two consecutive troughs. That is also called the wavelength. Wavelength is designated with one symbol like this. This is called lambda. I don't know, lambda is LAMDA. I think it's LAMDA, not
But
D.
lambda, sir.
Lambda,
Yes, sir.
correct. This is correct.
LAMBD.
Yeah.
Okay, fair enough. So it is designated by this Greek letter lambda. Okay. What do you think will be the unit of wavelength, guys?
So
Meters.
meter only, no?
Meter, because this is like a distance, na? So the unit of wavelength is going to be meter. So sometimes, no, they will ask you in a slightly different way. Okay, I will just tell you.
So can you explain what lambda is again?
Lambda is nothing but wavelength, and its unit is meter.
Yes.
What is lambda? It is the distance between two crests a consecutive crest, that is the peak point, or two troughs, or the bottom point, or starting to ending. Okay.
Yes.
So now look at this, the compression rarefaction diagram. Supposing I put this distance. Tell me, what is this distance now, which I have marked here?
1 lambda.
1 lambda, because you see here, this is like the peak. Okay. So if I were to look at this in the form of the pressure time diagram, this is the peak here, some peak. And what about this point? This point is representing the trough. Okay. So from the starting point to the ending point. So this is nothing but one wavelength. Okay. It is also this, see, this is one trough here, beginning of the trough. And this is the second trough, trough to trough. So this distance also is lambda. Okay, so if I just were to draw this diagram here, this is one trough, then there is a peak, then there is a trough. So if you see this point and this point are one and the same. Okay, hold on. Yeah, so this point out here corresponds to this point. And then here there is a peak here. This is a peak here. This peak corresponds to this point. And then there is a one more trough here. That trough corresponds to this point. Okay. So that means this distance now is trough to trough. Okay. So if someone gives you this compression rarefaction diagram, okay, you should be able to identify the wavelength from these kind of diagrams too. Are you following this, guys?
Yes, sir.
Okay. So let me ask you one more question. Is this wavelength?
Yes, sir. It can be called wavelength.
Think carefully and tell me.
So which
So you're
Because
moving.
see,
No, sir. No, sir.
no, because see, this is the beginning of the high pressure. This is the ending of the high pressure. So try to plot this in the form of a graph here. If you draw the graph,
not touch the
yeah, so this is the peak position, na? And this fellow is the peak position. Okay. So this is the beginning of the compression. This is the peak here. Here, this is the ending of the compression. Okay. Then this is the rarefaction region here. And then once again, you have the peak. This is the peak position. This is the ending of the peak position. So here I seem to be asking from the beginning of this to the ending of this. Like this here. Are you following this, guys? So there are two peaks here, this and this. And then from here to here, this is the compression cycle, but not full high pressure. Okay, it is decreasing compression. And from this here, beginning of the compression to the peak. Beginning of the compression to the peak. So if you see this, this is not the wavelength. Okay. Whereas if I say this, array, this is the peak, this is the peak. Right in the middle of the compression. Then this is the distance between two peaks. Are you getting this, guys?
Yes, sir.
Okay, this would be the wavelength. But the first diagram the first measurement which I put, that is not the wavelength. Aryan, are you following this?
Yes.
Okay. Similarly, just for rarefaction also, if you see here, this is the in between the rarefaction cycle. Okay, because this whole thing will be like this. Hold on. So this whole thing is the rarefaction. This is the peak of it. Okay. So if I say this is the bottommost point, this is the bottommost point. If I measure this also will be lambda. Are you getting this, guys?
Yes, sir.
Okay, this is this wave. Then this is this wave. All right. So my whole point is that you should be able to visualize peak to peak and trough to trough and identify the wavelength even in when you are given these kind of diagrams, compression and rarefaction diagrams. Okay. In fact, this kind of a wave is called a longitudinal wave. This kind of a wave is called a longitudinal wave. Okay, we will define what is a longitudinal wave. Okay. So, if you look at it now, we are talking about the vibration of particles. There are two things which you need to identify. Okay. First is, how are particles of medium vibrating? Along which direction? Can you tell this to me? How are the particles of the medium vibrating?
Sir, from left to right.
Left to right, isn't it? So if you look at it, it is the x-axis. Okay. So you can say along x-axis, the particles of medium are going like this. From one, we saw that red dot. No, red dot is moving from left to right, x-axis. Okay. Then second question is, how is the wave traveling? How is the wave traveling?
Up and down.
No.
Sir, again left to right.
Yes, sir. Left to right.
That also is from left to right. No. So, Ribu, little confusion for you. Okay. So I will just sort it out for you. So you look at this. Are you seeing that animation once again?
Yes, sir. Yeah.
Okay, look only at the top diagram, top half of the diagram. Okay, so this is what is actually happening in the sound wave. Okay, where when the drum is vibrating, the particles like the red dots are going left and right. And if you see the dark lines which are moving, that is called the propagation of the wave. Okay, so this particular thing is the propagation of the wave. Only look at the top diagram. Okay, so the bottom diagram is our graph. The actual wave is not like this. Actual wave is like top, where the particles are moving and the compression is going from side to side. This is like the water ripple. If you drop a stone, this kind of wave is formed. So don't get confused by that.
That's why I said up and down. Yeah.
Okay. So when you just the top half of the diagram which you are seeing, that is the sound wave actually. Aryan, are you confused?
No, sir.
No. So when you say sound wave, no, you just put your hand here and you say ba or you say pa pa. You can feel the pressure of the air against your hands. That means the air molecules are vibrating in the x and y x direction, and the wave is also moving in the x direction. Are you following this, guys? Don't worry about how we represent. We are representing it like the sine curve. But actually, how is this sound wave? The sound wave is like this. Okay, this is how the sound wave is. Okay, this is called the longitudinal wave. Okay, so what is that longitudinal wave means? Bhaiya, the particles of the medium are vibrating in one direction. The wave is also traveling in the same direction. So the vibration of the particles and direction of propagation are the same. Okay, which means that vibrating particles and direction of propagation are in same direction. So such type of waves are called longitudinal waves. And an example of a longitudinal wave is the sound wave. So Shreya, what is a longitudinal wave, ma?
Sir, the vibrating particles and the direction of propagation are in the same direction.
First class. Okay. Whenever you have a energy transfer, that means you are talking about an energy transfer in which the particles of the medium and the direction of propagation, both of them are happening along the same direction. In this case, it is x-axis. Such waves are called the longitudinal waves. Example of longitudinal wave is our sound wave, which we are talking about. Okay. Then we come to another kind of wave. Okay. Have you guys made a note of this?
Yes, sir.
So supposing I take water particles. Okay. So supposing these are all the particles of water in a lake. Okay. In fact, I will try to get one animation for that also. It helps us to visualize. And now I drop a stone here. Okay, so the stone is going to descend down and it is going to cause a ripple, right? So can you guess and tell me how the particles of this water vibrate when the stone is dropped on the lake? How will these particles vibrate? Tell me, guys.
So they'll vibrate like in circles, like around stone.
So it vibrates up and down, but up and down movement will cause the ripple to form.
Up and down motion will cause the ripple to form, isn't it? So I'm sharing my screen here. Hold on. Can you see the screen now, guys? Confirm to
Yes,
me
sir.
once you're able to see it.
Yes, sir.
Okay, so if you see the transverse waves, no, there you saw the particles in the PPT animation which I showed you, they were going left and right. But if here you see the when you drop the stone, the particles are going up and down. Correct, huh?
Yes.
Okay, but if you look at the bottom animation where the blue color thing, you see that you look at the ripple only. How do you think the ripple is moving? Which direction ripple
In
is moving?
circular motion.
No, ripple, top part you see, the wave actually. How do you think the wave is going?
It's moving both transverse and longitudinal.
So from right to left, right?
The wave, how do you think wave moves in a lake, Aditya?
Sir, right to left.
Right to left, isn't it? That means in the case of a transverse wave, okay, when you drop the stone down, right, the particles of the medium, that is here the water particles, are going up and down. Okay, so if I can just draw this here for you. These guys will go up and down. Okay, but whatever that ripple that forms, that ripple is going to propagate in this direction. Okay, so we say that, but yeah, this is the direction of propagation of the wave. I think it is propagation, direction of propagation, whereas up and down, this is the direction of disturbance. Are you guys following this?
Yes, sir.
Okay, so what will you call these kind of waves?
Transverse.
Transverse waves. Okay, these kind of waves are called transverse waves. Okay, so Arin, can you define what transverse waves will be for us?
Sir, like which our side. So it goes on the opposite side whenever a disturbance happens.
You should not say opposite. What is the direction which we said? Opposite.
Sir,
Opposite.
right to left.
No. There are two things how you can describe waves. Okay. One, you should use the term direction of the disturbance of particles. Okay. And the second thing you should say direction of wave, propagation of the wave. Means how is the wave moving? Okay, particles movement, wave movement. These two terms you have to use. And you have to describe transverse waves. How will you do that?
So the direction of propagation will be opposite.
Don't say opposite. How is the direction of propagation here?
Sir, right to left.
Disturbance, direction of disturbance.
So do you want to say perpendicular?
Up and down. See, here the particle is going up and down, isn't it? Like this. ऊपर नीचे जा रहा है. Vibrate. The particles are of the water molecules are going up and down, whereas the wave is going left to right. Are you following this, guys?
Yes.
So, how you define transverse waves are when the disturbance of the medium and direction of propagation are perpendicular to each other. Okay, then such a wave is called transverse wave. Are you following this, guys? Mr. Natkarni?
Yes, sir.
You know, we all have our spring mattress, no? Like the trampoline. If you go and sit on the spring mattress, how will the springs compress? They will be going up and down here under our weight, like a trampoline. Okay. But if you look at the wave which is formed because of that, the ripple, that ripple will start at one point and it will seem to reach the shore, isn't it? So you will say the ripple is going along the x-axis, whereas the water particles are jiggling up and down, perpendicular to the direction of propagation of wave. So whenever the distance of disturbance of the medium and the direction of propagation, they are perpendicular to each other, such type of wave motion is called transverse wave. Example, the waves formed in a lake when a stone is dropped.
Yes, sir.
Example, the water wave when a stone is dropped. We don't say ocean because there is so much disturbance you can't see. Okay. For us to understand the concept, you have to take a still lake and drop a pebble. Then you can see that. So, Aditya, tell me what is a transverse wave? Proper definition.
Yes, sir. A transverse wave can be defined as a wave which is formed when the disturbance of the medium and the direction of propagation are perpendicular to each other.
Yeah, perpendicular to each other. Give me an example for that.
Sir, the ripples formed in the water after dropping a stone in a lake.
Yeah. So when a stone is dropped in a lake, the water particles are going to go up and down, like the mattress springs, upar niche. They go up and down, and when they go up and down, they displace the water. So the water will come up. Okay, that is the formation of the ripple. Whenever the water particles move up, they form the ripple. So if you are going on top of the lake and observing, that ripple seems to move along the lake. We call that as the horizontal direction. But if you go inside under this lake and observe the particles, if you are like a dolphin or a fish, you can see that the water particles are jiggling up and down. So we say, Bhaiya, water particles are moving up and down, but wave is going along the water. Okay, so such kind of a perpendicular this thing is called a transverse waves. Okay, so in fact, if you show the transverse wave, transverse wave also you will show like this only. Okay, but what would this in the transverse wave mean? What will be the y-axis here? And what is this measure going to be? Here also, is it going to be pressure?
Will that be the height?
Correct. This is the height of the wave here. This is not going to be pressure. Okay. This is actual movement of the water particle. Okay. So this is the height of the wave, or this is the distance basically. And this is going to be time. Are you following this, guys? Okay, here we are actually measuring the distance that the water particles move up and when when they move down. Okay, so this is in the y-axis. We are not measuring pressure or anything. We are actually measuring the physical movement of the particles as they vibrate up and down. Okay, but all the definitions are the same. We are still going to call this as amplitude, right? We are still going to call this as crest. We are still going to call this as trough. We are still going to call this as wavelength. Everything is the same. Okay, only thing is what you are showing in the y-axis is going to be distance of the particles moving from mean position to top position. That is called amplitude. And this is from mean position to bottom position. Okay, this is called trough. But this height is amplitude. Did you guys follow this?
Yes, sir.
So what we are doing is, this is easy for us to visualize, okay? Then we are telling, yeah, when transverse wave so easy for us to visualize, why can't we show the compression rarefaction wave also in the same way? Let us depict, okay? Let us depict the sound waves also in this fashion, because it is very easy for me to understand. Okay, so whenever you show a sound wave like this, sound wave is not a transverse wave, isn't it? Sound wave is not a transverse wave, but yet we depict as if it is a transverse wave. Are you following this, guys?
Yes.
So we are making use of this depiction in the transverse wave for the sound wave also, but we are measuring the pressure. We are measuring the pressure and we are showing the variation of pressure. Okay, and we are depicting that longitudinal wave also like a transverse wave.
Sir, can you scroll up 1 second?
Yes, I will. What is it you want to make a note of?
Yeah, I saw something I don't know what it is.
Which one? Appa.
Yeah.
Sir, it looked like a
Appa, some my
mouse,
doodles. I was doing some theory of it.
No, I saw a rat somewhere.
Yes, sir. There's some rat.
Sennheiser Airport, something, yeah, scientific visualization. I gave you some Gyan last class, no? Understand, learn slow. Something, my own doodles. I take pains to see how to teach you, what are the best practices and all that stuff. Okay, so Ribhav, can you tell me what is it that I am taking pains to explain to you?
Sir, what do you mean?
Abhi itna, whatever I spoke, what is it I'm trying to explain to you?
Wave movements, visualization, sound particles.
Not like that. Aditya, what is it that I'm trying to explain to you?
How you visualize what you learn?
No, no, no.
Sir, do you want it as in terms of a teaching practice or in terms
No,
of
no, not like that.
physics
See,
lesson, sir?
what we are telling is, yeah, see, this is like a sound wave, isn't it?
Sir, are you trying to show how the different types of showing a wave?
So, okay, let me tell you. So, this is a sound wave. Sound wave is a longitudinal wave, correct, na?
Yes, sir.
Longitudinal wave and transverse waves are different, isn't it?
Yes, sir.
Yes,
We
sir.
saw that. The sound wave is a longitudinal wave, and we have seen the animation, how the sound waves get generated. Okay, but when you're depicting them, you're depicting them like this. Okay, what is this? This is generally how transverse waves, this is how they show the transverse waves, isn't it? So, sound waves are longitudinal waves, but we are depicting them as if they are transverse waves. So you will get confused. But sir, sound waves are like, they are moving horizontal and wave is also in the same direction. Just now you told them transverse waves. How can you depict them like a longitudinal waves? How can you depict them like a transverse wave? That doubt will come, isn't it? Because whenever you see this, this is actually for water particles, the way the wave travels and all that stuff. Okay. So the reason why we are doing it is easy for us to visualize. Okay, and here we are trying to measure the peak pressure, and this is the low pressure, and we are showing pressure here in the y-axis, and here we are going to show the distance here. Okay, so when we are translating pressure and putting it in the y-axis and distance on the x-axis, our longitudinal wave can be visualized like a transverse wave. Does that make sense?
Yes, sir.
Okay, because the correct way for me to show the transverse wave would be like this. I will say, Bhaiya, this is the transverse wave. Hold on. Am I showing the PPT to you?
So this is a one more.
Okay. This is what I am trying to showcase to you. Okay. Sound wave is the top, but the way I am showing it is like a transverse wave, like a water wave.
Sir, is it a misconception?
Not misconception. It is for easy way of understanding. Because if I show the top wave to you and tell you, show me the amplitude, show me the time period, show me the frequency, it is difficult for us to visualize. Okay, with all the dark bands and light bands. Okay, but the minute I measure the pressure and I show it to you like a water wave, the transverse wave, it becomes easy for us to understand. That means longitudinal waves are represented as transverse waves. But are longitudinal waves like transverse waves? No. Only for visualization purpose, I am showing it like this. Are you
Yes,
able to follow this?
So it's made to make it easier.
Connection is easier. Okay. Because what is very intuitive is the bottom graph, you visualizing the water particles, the actual wave which we all know through experience, where the particles of the medium are up and down and wave is propagating like this. That is what is the bottom graph. Very easy for us to make out. It is a typical transverse wave. Okay. But what we have done is, because it is so easy, we are converting, if I can use the word, we are converting the longitudinal wave and we are visualizing it as a transverse wave. Are you following this?
Yes, sir.
Okay, that is what I'm trying to make it clear for you. Ribhav, did you follow this? Okay,
Yes,
can you
sir.
just explain in 1 minute what is it that I'm trying to explain since
So
last
they're
2
saying
minutes?
longitudinal and like transfers of waves are not the same. They're
Ah,
different, but we do this to help you like visualize better. So like we are representing it as like this because you can like visualize that these waves are moving like that.
yes.
Like when what they actually are is not like that. It's just
Yeah.
a
Okay, so by measuring the pressure, okay, and depicting it in the y-axis, okay, we are converting what is a longitudinal wave and visualizing it as if it is a transverse wave. But we know that longitudinal sound waves are actually longitudinal waves. Okay, so that's what is the thing. Okay, so would you like to take a short break and come back, guys? Then I will show you one experiment and we can take the discussion forward.
Thank you, sir.
What will be the unit of frequency, guys?
Oscillations per second.
It is Hz, Hertz.
Hertz.
Very good, Hertz. Hertz is the unit of frequency. One a capital H you put and one Z. Over on. Shreya, tell me, Ma, what is time period?
The time period is the time taken for one wavelength or for one oscillation.
One complete oscillation. Okay, and what is frequency?
A frequency is the number of oscillations that take place in 1 second.
In 1 second. Very good. Okay, so try this. Okay, if frequency of tuning fork is 100 Hertz. What will be its time period?
Yeah, should we send the answer in the chat?
Huh?
Should we send the answer in the chat?
Okay, you can text me, yeah. If frequency of tuning fork is 100 hertz, what will be its time period? I got one answer from Aditya. Ribhav, are you there? Or slept off? See, Ribhav is not there. I caught him.
Sir, I think he's gone to fill up his water bottle.
He gone for?
He texted me saying that he went to fill up his water bottle.
Okay. What meant Tanush? What will be the time period?
So is it 1.66?
No. Shreya, what will be the time period? So, see guys, we are telling, when you say frequency of tuning fork is 100 hertz, what does that mean?
So, but we need the distance or something, we need extra information there.
Oh, that's what I'm telling. When we are saying frequency of tuning fork is 100 hertz, what does it mean?
Vibrates at 100
Sir,
hertz per second.
Frequency is 100 hertz means what? What is frequency? Tell me.
Oscillations per second.
That means we are telling the tuning fork is having 100 oscillations, correct now?
Yes.
In 1 second. Isn't it? When we say frequency is 100 hertz, we are telling, yeah, this tuning fork is having 100 oscillations in 1 second. Okay. What do you mean by time period?
so 1 second.
So
1 second number of oscillations is frequency. One oscillation, how much time is time period? Are you able to follow this, Aryan?
Yes.
100 oscillations, 1 second. One oscillation, how many seconds?
So it'll be like 6,000.
Day. 100 is happening in 1 second, Ra. For example, 10 is happening in 1 second. 10 times oscillation is happening in 1 second. One oscillation will take how much?
So it's one oscillation like 60 seconds. I'm not understanding.
Where do I go and hang myself? Ceiling fan, okay, good only. Because I can't, I have to hang myself. Aaron, what the unitary method? Tell this fellow, no? I can clap, Tanush, I can clap 5 times. in one-
Understood, so sorry.
What understood? Tell me, no? I can clap 5 times in 1 second, man. What is the time taken for me to do one clap?
Understood, sir. One oscillation.
Oh, what is the time taken for one clap?
1 second.
1 second. Now. Yeah, I can do 5 claps per second, Ray.
Can you repeat your question, sir?
Hold on. क्लास में हूँ यार. हाँ बोल ना. No, I conveyed to Vinay. Vinay said it's all perfectly fine. Just tell him that. I told him you're traveling also. Vinay is perfectly happy. He's fantastic. Tanush, Anand does 5 claps every second. What is the time taken for one clap? Okay. Anand is able to do 2 claps in 1 second. Can you just clap 2 times in 1 second?
Sir, 1 second.
In 1 second, you are able to do 2 claps.
Yes, sir.
What is the time taken for 1 clap?
Sir, 0.5 seconds.
Huh?
Sir, 0.5 seconds.
How did you do it?
Sir, unitary method.
How did you do it?
Sir, 2
Okay.
by 1 second.
2 by 1 now.
1
2 by
divided
1 is, how can 2 by 1 be
by 1
0.6?
divided by 2, sir. 1 divided by 2.
बस थोड़ा मैथ का ख्याल रख यार, नहीं तो बेचारे मेरे जैसे फिजिक्स टीचर्स मर जाएंगे यार. हाँ, 10 claps in 1 second, 1 clap, how much time you take? Last 10 minutes we are discussing today. तुम लोग next time 10th में रहोगे next year. It's like 12 apples is costing 10 rupees. What is the cost of 1 apple? Okay, anyways. Guys, do I need to explain to anyone? Aryan, what will it be, bro? 100 oscillations in 1 second. 1 oscillation, how much time will it take?
Sir, 100 divided by 1.
He is Tanush's friend. 100 oscillations happening in 1 second, Ray. 1 oscillation, how much time will take, man?
Sir, 100 seconds. Sir, can you repeat your question?
You heard it right. Can you just tell me what you heard?
Sir, in 1 second, how many oscillation will come?
नहीं, आर्यन, ये देखो मेरे बच्चे, मैंने यहाँ पे you speak Hindi at home, huh? I will speak in different languages, okay? ये जरा पढ़ो please. पढ़ो ना, जोर से पढ़ो.
100 oscillation in 1 second.
हाँ, 1 सेकंड में 100.
Oh, 10 oscillation will be 100 divided by 10.
10 नहीं, this is 1.
Oh, 1.
हाँ. एक काम करो, तेरा नोटबुक में लिखो एक बार. Open one notebook. Please, for my sake, write it down. मैं यहां से किचन तक 10 बार जाके आ सकता हूं 1 मिनट में. You imagine yourself going to kitchen and back to the seat. Okay, you are doing 10 times in 1 second. Imagine करो, फुर 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 करके जाके आ रहा है. एक बार जाके आने में कितना टाइम लगेगा? That's the question.
Repeat your question.
Aryan is able to go from his seat to kitchen and back 10 times in 1 second. 1 सेकंड में 10 बार जाके आ रहा है. एक बार तुझे किचन जाके आने में कितना टाइम लगेगा?
Sir, 1 by 10.
मेरा जान बच गया रे बाबा. ठीक है, थैंक यू. मेरी लाज तुमने रख दी, मैं बच गया, नहीं तो मेरा नौकरी चला जाता था. अरे हाँ, तो थोड़ा ना मैथ, यूनिटरी मेथड, सिंपल अलजेब्रा वो सीख के फिजिक्स क्लास में आया करो यार. नहीं तो तुम्हें किचन भेजना पड़ेगा, फर्स्ट फ्लोर भेजना पड़ेगा, बाथरूम भेजना पड़ेगा. Okay, I'm just having fun with you, okay? Sometimes it can get a little tricky, okay? So 100 oscillations happening in 1 second. Therefore, 1 oscillation, how much time it will take?
1 by 100.
Is equal to 1 by 100 second. Okay, that will be 0.01 seconds. Okay, so time period T is equal to, the formula for it is like this: time period is 1 by F. I don't want to tell that, I wasted my time, because if I tell this now, you'll forget it. You have to know what you mean by 100 frequency, and then be able to connect frequency with time period. Time period is 1 by frequency. Did you guys make a note of this formula? How are time period and frequency related? Time period is equal to 1 by frequency.
So 1 second.
Now don't tell me 1 second. I will get heart attack.
I'm noting on the.
Note down.
Third.
And please write this example. Shreya, did you follow this, ma?
Yes, sir.
Okay. Now, second question. If time period is equal to 0.25, okay, what will be the frequency?
Sir, I sent you the answer in chat.
Okay. Can okay. Ribhav, can you explain how to do this part?
Sir, time period is 1 by frequency. So 0.25 is equal to 1 by f. F into 0.25 is equal to 1. 1 by 0.25 is equal to frequency. 100 by 125, 4 by 5 are 0.8.
How, man? You told the complete story correctly.
4, sorry.
Huh?
Sorry, it's 4. 100 by 25, sorry.
100 by 25 is a 0.8.
No.
You also have to brush up majorly.
No. Sir, I wrote correct, sir. Sorry.
I saw your chat window.
No, sir, I wrote correct only. Sorry.
Okay. So time period T is equal to 0.25. 0.25, always think in terms of fraction, 1 by 4. Okay. Then I know T is equal to 1 by F. Therefore, F is 1 by T. Therefore, F is equal to 1 by 1 by 4. 1 by 1 by 4 means 4. Okay. Any questions with this, guys? What will be the units, sir? For what?
Hertz, sir.
Hertz.
This is 4 hertz. Hertz is nothing but oscillations per second. When someone says hertz, what is hertz? Hertz is the unit for oscillations per second. Okay, that means whatever motion I am describing, whose time period is 0.25, okay, that will make 4 oscillations, 1, 2, 3, 4 in 1 second. 4 oscillations per second. Okay, so that is what is called the frequency and time period. Okay, all of you clear with this now? Then one more concept or formula which I want to talk to you about is called velocity of wave. Okay, see this velocity of the wave you can understand using one simple example, guys. Okay, you think of this fellow. Do you know this guy Bolt?
Yes, sir.
What is his full form? I forget.
Usain Bolt.
Usain Bolt.
Usain.
Usain Bolt. Usain Bolt. Okay. So what this Usain Bolt can do, no? If you see fast runners standing in their place, they'll do taka, 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 they will move their legs, isn't it? I don't know what it is called. Jumping on the same spot. Okay. That fellow can do 30 jumps, let's say in 10 seconds. Or let's keep it simple. He is able to do 3 jumps per second. Okay, 3 jumps means, you understood what I'm saying, no? Left, right, left. 3 times he's able to move his. In fact, for all the quickies, that is like an exercise. Even football players, they will do. On the spot, they will have to move their feet quickly. Okay, up and down, up and down. And his stride length, Usain Bolt's stride length is, let's say, 4 meters.
What is
Okay.
stride length, sir?
Stride length, bro. Stride length.
Like running stride length.
Stride length means are you able to follow this? Stride.
Distance
Stride
between
means
his feet.
not speed. If I stand one place, the next and my other foot is somewhere.
No,
What
sir,
is
the
the
distance
distance?
between his feet.
Feet. Stride means what? If I'm running if I'm in the process of running, right? Short fellows can not go from one place to, they cannot have a large stride length, isn't it? They will go from here to here. Short fellows. Long fellows means, okay, their one leg will be here, or another leg they will put here. They will have a long stride length, isn't it? So if you are a
Yes.
walker, if you are a tall person beside you, they will easily overtake you because their stride length is very large. Okay. Short fellows will have short stride length. Okay. Now, can you tell me what will be our Usain Bolt speed here? Given both the data, what will be Usain Bolt's speed?
12
12 what?
12 meters per second.
12
Meter per
meters
second.
per
per
second.
second.
Very good. Okay, because see, this fellow is able to move his legs 3 times in 1 second, isn't it? One left, one right, one left. On the spot, he is able to do. And supposing he starts running, we expect that he will be able to do the same thing. Okay, so he will be able to put 3 strides. Each stride is 4 meters. That means he can manage a speed of 12 meters per second given the data. Okay. So with this example, can you tell me what will be the formula for velocity? Velocity of wave.
The
The current
distance
distance by like
Distance.
by time.
That we all know, Ray.
So distance by
Not by.
isn't it
The
into?
frequency
Yeah,
into frequency into lambda.
Frequency into lambda, isn't it? See, what is the stride length compared to? This stride length is like lambda, isn't it? Distance. And what is 3 jumps per second equivalent to? Frequency, isn't it? And v is the velocity. So we can say v is equal to frequency multiplied by lambda. Frequency is like number of jumps per second. And for each jump, how much distance you will travel. That is wavelength, isn't it? So velocity is nothing but the number of jumps multiplied by stride length. Or v is equal to f lambda. Sometimes, no, frequency, they also say n. So v is equal to n lambda. N is the frequency. So
The same thing
whatever
I said, but like, I mean, multiple by time is 1 by f, so you put the f that side.
time is 1 by f. Yeah, you can do that also.
I said v into t.
V into T.
Yes, sir. Is equal to lambda.
Time period.
Yeah.
You learn it as V is equal to N lambda. Okay.
Yeah. Okay.
Because when you say V into T, this here is not time. This is time period. Okay. T and time period are different. Time is just seconds. Okay. When you say time period T, this is how many, what is the time for one oscillation? Okay. So here capital T is not equal to small t. Reba, are you able to follow this?
So 1 second.
Huh.
Yes. Sir.
Okay. So I was saying that when you say V into T is equal to lambda, while F is equal to 1 by T is true, when you say here V into T is equal to lambda, you should be careful to know that this is not T, small t in seconds. Okay.
So time period, I know.
Yeah, this is capital T, time period. Okay. Time taken for one oscillation. Okay. So
Okay.
it is different. Unit wise, it may be seconds only, but capital T is different than small t.
No, yes, sir. I know that.
Okay. Because see, when we say velocity is equal to distance by time. Okay. Here, this distance, this time is time for traveling this distance, whereas this T is time period.
This is time for the vibration.
One oscillation.
Yeah.
For one vibration. Are you guys okay with this?
Yes, sir.
Okay. I think we're almost done with time, but I will just try to tell you one or two small tidbits, then we can move ahead. So, what is the speed of sound in different medium? We will see that, okay?
Fastest in solids, lesser in liquid, least in gas.
You learned, okay. So, speed of sound in air, you tell me how much is this?
330
380, like 330.
I think 330 is correct.
Yeah.
Approximately 330 meters per second. Make a note of this. Speed of sound in air is 330 meters per second. Shreya, are you still with us?
Yes, sir.
Okay, ma'am. Sometimes I just do that. For ICSE guys, you need equations and all. I will take separately for you. Okay.
So what equations?
The dependence of speed of sound with the pressure, density.
Oh yeah, pressure won't affect density. Is like
all that stuff. That separately I'll teach you, Ranveer and others. Okay. Then speed of sound in water. First, can you guess whether sound will travel faster in water or slower in water?
Faster,
slower.
the molecule.
Hey,
Slower.
Sir, faster.
Sir, it
Slower.
will be faster.
Okay.
Faster. So
Faster,
faster because
sir.
molecules are closer, so it'll vibrate faster.
So see, air, no, the particles are not very closely packed. Okay. They have a lot of, because it's a gas, the distance between the molecules here is large. Okay. So time for transferring the energy is higher. Okay. Whereas water, the molecules are more densely packed than in air, isn't it? So easy for me to transfer the energy from one oscillation to the next, one vibration to next. Okay. Because of that, the speed of sound in water is greater than speed of sound in air. Are you following this, guys?
Yes, sir.
Okay. In fact, its speed is approximately 1480 meters per second in water. These are sometimes for air, they may say 333. Okay, sometimes they may say 420, 320, but approximate value is 330 meters per second. Like that, here also approximate value is 1480 meters per second.
Sir,
Okay,
it is opposite for light.
opposite for light.
Yes,
Light
sir.
doesn't need a medium for to travel, doesn't.
Correct. Light, no medium is required, bro.
Sir, air is required.
For light,
So how air is required? Not required.
for light, Baba, that's what we were discussing with Ranveer the other day. Light, no.
Temperature, sir, not medium.
Light, for
Need
example,
medium.
sun's rays are coming to you, no? There we have space in between. There is no air, nothing. How are you getting light from the sun? Isn't it? Here, the sun's rays are traveling, no? And reaching Earth here. Only in Earth, here we have atmosphere, or you can say air. But all this distance, millions of miles, it is space, isn't it? So space does not have any molecules. It is, we can say it is empty. Okay. Space is empty. It doesn't have any molecules or any medium. But light can travel without medium. Are you following this, Aryan?
Yes.
It doesn't require air. It doesn't require any medium. Okay. So this is called radiation. Radiation means when you are able to transfer the energy without the presence of any medium, we call radiation. So light reaches us through radiation. But if a sun is making any sound, no grumbling sounds, okay, that those sounds will not reach us, because
Yes,
for
that
that
reason.
sound to reach, we need medium.
Yes.
Are you following this, guys? So,
Yes, sir.
what do you think will be the speed of sound in metals?
So the
Let's
fastest.
That of water.
Fastest because the solids and
Because
molecules
the
Because
sound-
it's the most tightly packed.
will be able to vibrate.
Okay, so different fellows will have different, but if I take steel, it is around 5,000 meters per second. Approximately, it's not exact. And different metals will have different speeds, but you can say around 5,000 meters per second. Okay, so it is faster than water also. Okay, so people will say, hey, how is it that you can predict the train is coming even when you can't
So
hear
the
it?
sound comes from the track.
You
Ah.
put your ear close to the railway tracks and then you can
Yeah.
hear.
So if you put your ear on the railway track, okay, so the train may be far away, you can't, maybe 10 kilometers away, you can't see it, but the vibrations that the train is producing, no, will travel through this faster than the train can travel, isn't it? The train is coming here at maybe 56 kilometer per hour or 36 kilometer per hour, 10 meters per second. That is the speed of the train. Okay. But the sound waves through the rails will travel at, let's say, 5,000 meters per second. Okay. So you can, even when the train is far away, you can hear the sound of it and you can say, Bhaiya, train patri pe aa rahi hai, whatever. Okay. So with that thought, we will end this class. Wish you guys very nice Dashara. Tomorrow we are having a holiday. And I will give you a small assignment now because we discussed characteristics of wave, amplitude, frequency, time period, velocity of the wave, formula, okay? Longitudinal transverse waves. We can do one assignment by next week, okay? Chalo guys, thank you so much. Bye-bye.
Sir, tomorrow there's no class.
Tomorrow we are giving off for Dashara 1 day, bro.
Okay.
It is
Thank
the
you,
end. Okay, so we will catch on later. Huh?
Yes.
But please do the assignment which I am giving without any delay.
Okay.
Chalo, bye bye.
Thank you, sir. Bye.
Okay, sir. Bye.
Bye.